Welcome to Curium. As part of Tool 1, you are expected to be able to determine the empirical formula of a substance using the mass changes which you obtain from a combustion reaction. Note that the concept of empirical formula could be assessed in paper 1A or in paper 2, but the experimental perspective of empirical formula is most likely to be found in paper 1B. There are some key concepts that will be helpful if you understood before we begin. What is an empirical formula? What is a combustion reaction, and how is it different to an incomplete combustion reaction? Also today, we will mention systematic error and percentage uncertainty, but note that anything to do with error and uncertainty is often found as part of a multi-part question in paper 1B. The setup of the experiment typically looks something like the image which you can see on the screen, which shows a crucible holding magnesium ribbon being heated strongly over a Bunsen burner. Before this is discussed any further, we need to first identify some of the risks associated with this experiment and ways in which you would need to prepare the magnesium ribbon before you begin. The first thing to note in terms of risk is that obviously because you are heating the entire apparatus, it's going to be hot. So you would take care to hold things with tongs or else just to wait until everything cools before you begin to handle it. The second thing to note, this reaction is highly exothermic, which means that a lot of energy is being released. When you open the crucible lid, in order to allow oxygen to enter to ensure that combustion is happening, you will notice that at the point of combustion, the magnesium burns very, very brightly, emitting intense UV and visible light. This can actually be quite damaging to your eyes, so for this reason, you would not stare directly at the glowing magnesium ribbon while it is combusting. Methods will often ask you to use sandpaper on the magnesium ribbon or to file it before you begin. That's because the magnesium ribbon will react with oxygen in the air anyway, and so you'll end up with a layer of magnesium oxide on the surface of the magnesium ribbon. You want to begin with pure magnesium. So for this reason, what you try to do is sand off all of that layer of magnesium oxide before you begin, so that you just start with the pure magnesium. Throughout this experiment, you'll make 3 main mass measurements. The first thing you'll do is you'll measure the mass of the crucible before you begin, when the crucible is empty. Then you will add the piece of magnesium ribbon and get the new mass. The difference between these two values is obviously the magnesium itself. Then you'll heat it. Once that silver magnesium ribbon has turned into a white powder, you know that it has turned into magnesium oxide, and then you'll take the new mass. The difference between these two values is now the oxygen. You will collect raw data that will look something like this, similar to what we just discussed. Notice here the qualitative data are the observations that were noted. The grey shiny appearance of the magnesium to begin with, and the fact that you end up with a grey-white powder at the end. This is the data that you will now use to determine the empirical formula of the magnesium oxide. The difference between the first 2 mass measurements is for the magnesium. This has a difference of 0.05 grams. The difference between the second 2 measurements has a difference of 0.03 grams. This is for your oxygen. Now we will go ahead and process this further. As we now know the mass of each element present in the compound, and we know the molar masses of each because we can just read that off the periodic table, we can then use that to determine the number of moles using the formula N is equal to M over MR. Once you do that, and you have the number of moles of each one, you'll need to make these into a whole number ratio. To make them a whole number ratio, you just divide them both by whichever number is smaller. Now that I know that they're in the ratio of 1 is to 1.02 for magnesium to oxygen, I can approximate that to a ratio of 1 is to 1. And therefore I can conclude that the formula is MgO. Notice how this can be linked to Tool 3 mathematics, where you know how to use approximation and estimation when it's appropriate. After that, you need to discuss why the ratio isn't the perfect 1 is to 1 MgO ratio that you would expect. Think about what we know about magnesium and oxygen. Magnesium is in group 2, and things in group 2 always have an oxidation state of +2. And oxygen is in group 6, which we know always has an oxidation state of -2. So because the overall charges on the compound must be equal to 0, I would expect that the formula would be exactly MgO, and yet I didn't get that. So let's discuss some of the assumptions we made in our calculations and some potential sources of error. So the first thing we were assuming is that the magnesium was pure to begin with. So of course you used sandpaper to remove any of the residual magnesium oxide which was on the surface of the magnesium strip, but that doesn't determine anything about the magnesium under the layer. So we assume that the magnesium was pure. We also assume that the magnesium isn't reacting at all. That's a reasonable assumption, although in reality it probably does react to some very, very small extent. We also ignore the fact that soot was probably formed on the bottom of the crucible. Remember that soot is the product of incomplete combustion. And if your Bunsen burner has a sort of yellowy orange flame, that means that incomplete combustion is happening. If it's complete combustion, your flame would be completely blue. So if there's a small amount of black powder formed on the bottom of the crucible, that's soot, pure carbon. That will also impact the mass measurements that we're taking. Also, a large assumption. We're assuming that the only reaction that's happening here is magnesium and oxygen. But think about what you know about air. Air is composed of 78% nitrogen. So in reality, a limited amount of that reaction is happening too. So it's probably not just magnesium and oxygen making magnesium oxide. There's probably a small amount of the magnesium reacting with the nitrogen to make magnesium nitride. An example of a past IB question, which would be considered easy, would be which observation would explain a systematic error for an experiment which involves the combustion of magnesium to find the empirical formula of its oxide. A reminder that a systematic error is one which will affect results in one direction only, meaning that your results will always either be higher or lower than the true value. Remember, this entire experiment is based on mass, and mass changes. So anything that will have impacted your mass is what's probably going to have caused this error. When you heat the crucible, you do so using a Bunsen burner. Remember that for a Bunsen burner to be undergoing complete combustion, you should have a blue flame, and if there's a yellowy orange-red flame, that means you will have incomplete combustion happening. When that happens, carbon, or soot, is formed. That soot is a solid, and it deposits on the bottom of the crucible while you're heating it. So that when you measure, the mass changes, and you measure the mass of the crucible after heating, your mass is going to be slightly higher than it should be, because all of the mass change that you account as being oxygen is actually both oxygen and carbon. So because that will always cause your mass of oxygen to be higher than the true value, C is the correct answer. Another example of an easy paper 1 past IB question would be a student heated a known mass of zinc powder in an open crucible until there was no further mass change and recorded the final mass change. What would the student be able to derive from this data? So throughout this video, we've been talking about determining the empirical formula. The student can tell the simplest whole number ratio of zinc to oxygen in that compound. Because they know the total mass they put in and they know the mass changes, they'll also be able to work out the percentage composition. What the student cannot determine is the molecular formula. Although we know the simplest whole number ratio of elements in that compound, we don't know the actual numbers of each element in that compound. And for this reason, A is the correct answer. Now let's go through an example of a medium difficulty paper 2 exam question. Note that this exam question is worth 8 marks in total, so if you want to pause the video now and set yourself a 12-minute timer. The question tells you that when magnesium ribbon was heated in air, the ribbon reacted with oxygen to form magnesium oxide, and you have to write a balanced equation for the reaction that occurs. Remember that when you have a metal and oxygen reacting together, they will form a metal oxide. Take time and make sure that you form the metal oxide correctly, remembering that magnesium has a +2 charge and oxygen has a -2 charge. So for those charges to cancel out, you need one of each to form a neutral compound. Then make sure that you balance it. Here I'd need to add 2 here and 2 here to correctly form that equation. The second part gives you information surrounding mass changes, as we discussed earlier. So it was carried out in a crucible that had a lid, and the following data was recorded. So as we can see, the difference between the first and second points is that magnesium ribbon was added. So the mass difference there is obviously the mass of your magnesium. The difference between the second and third values is that now you have a product. So if the first 2 points is your magnesium being added, the difference between point 2 and 3 is your mass of oxygen, because now you've gone from Mg to MgO. Okay, if you're asked to calculate the amount of magnesium in moles that was used, based on the difference in those first 2 values, you know the mass of magnesium that was added. You know the molar mass of magnesium from the periodic table. So you can use that to work out the number of moles. That turns out to be 0.2614 moles. After you have that, you're asked to determine the percentage uncertainty of the mass of the product after heating. So we have to remember that each mass value has its own uncertainty with it. So if I'm getting the difference between those 2 masses, i.e. I'm subtracting, then anytime you add or subtract, you should always add the absolute uncertainty. So the difference between final mass and initial mass is 9.569 grams. And when I add those two uncertainties, it's 0.002 grams. So when I represent that as a percentage, it's 0.0209%. The next part asks you to assume that the reaction is the only one which is occurring and that the reaction goes to completion, but that some of the product has been lost from the crucible. Deduce the percentage yield of magnesium oxide in the crucible. Remember that percentage yield is a comparison between what you actually got versus what you should have gotten based on the amount that you put in. So I know from the very first part of this question that for every 2 magnesiums, it'll react with 1 oxygen and produce 2 magnesium oxides. So I know for sure the mass of magnesium that I put in. And I know that it will react in a mole ratio with MgO in a 2:2 ratio, which means that if I put in 0.2614 moles of magnesium, I should get out that same number of moles of magnesium oxide. So if I know how many moles of magnesium oxide I get out, or I should get out, then I can link that to the molar mass and use that to determine the mass overall, which turns out to be 10.54 grams. So this number represents how much I should have gotten based on how much magnesium I put in at the beginning. So I need to represent this as a percentage. So I put how much I actually got based on my experimental measurements, and you worked that out as part of the previous question. And I'm going to put that as a percentage over how much I think I should have gotten based on the mass of magnesium that I put in. That works out at being 91%. The next part would be the part that makes this question a little bit more difficult. So you're told that when magnesium is burnt in air, some of it reacts with nitrogen to form magnesium nitride according to the equation. We have discussed this previously. You're asked to evaluate whether this, rather than the loss of product, could explain the yield that you found. So what we're trying to explain here is, why is the yield less than 100%? And can we in any way link that to the chemical equation? So let's think about what I know already. I knew, based on the last part of the question, that if I was to put in 0.2614 moles of magnesium, what I should have produced was 10.536 grams of magnesium oxide. And that's if the reaction that I think was happening was actually happening, the reaction with oxygen. But based on the equation that you're given, if you were to put in the same number of moles of magnesium, then you should end up producing only 8.76 grams of magnesium nitride, which is obviously a little bit less. So that means that because the mass you did get was actually less, in fact it was only about 91%, it could make sense that this reaction could also explain it. If in an alternative scenario a different reaction happened, where it theoretically produced 12.5 grams, for example, a value that was over 10.536, then we would say no, this cannot explain why I've only ended up with 91%. The last part of the question asks you to suggest an explanation, other than product being lost from the crucible or the fact that it reacts with nitrogen, that could explain the yield. So potential things that the mark scheme accepted was that maybe an impurity was present that just didn't react, maybe your reaction was incomplete, or maybe your magnesium had already partially oxidized.